So let's record. Okay. So in this example, let's first process the data that we've been given, and let's try to understand a little bit about what's going on here. So first and foremost, we have an empty beaker. Okay, we know the mass is equal to 10.65 grams. So we have our empty beaker. Perfect. If we take our empty beaker and we drop in a metal sample, the mass is equal to 17.85 grams. So then, can we figure out the mass of this metal sample? Yes. So we can figure out the mass of this metal sample by taking 17.85 grams, which is the mass of the metal and our beaker, and subtracting the mass of the empty beaker. Now, as this is a subtraction operation, what do we care about? Sig decimal places. And looking at each of these numbers, they have how many decimal places? 2. So how many decimal places should our answer have? 2. Okay, let's punch this into our calculator really quickly. Oops, one moment. Here we go. So we have our calculator pulled up. We're going to take 17.85 minus 17.85 minus 10.65. Oops. 17.85 minus sign 10.65. And that gives us 7.20. So let's write that down. So we get 7.20 grams. Why do we have 2 decimal places? How many do we need to retain following sig fig rules? 2. If you just wrote this as 7.2, you'd be reporting an incorrect number of sig figs, and that will create a large amount of issues later on. Okay, so we have the mass of our solid metal sample. We can figure out the volume in the exact same way. So we know our volume initial in our graduated cylinder was 15.6 milliliters. So we have 15.6 milliliters. After we added the solid to the graduated cylinder, the final volume was 18.4. Now, this data is a key signpost for what experimental technique? What experimental technique involves measuring the change in volume before and after you add a solid sample to a liquid sample? What do we call this method? Let me draw it out pictorially here. Let's draw out a picture of this to get a sense of what's going on. So we have our graduated cylinder. And initially, our initial volume of water inside the graduated cylinder is recorded to be 15.6 milliliters. Okay? We take our solid sample, and we drop it into the graduated cylinder. Does that solid sample have a volume? Does it have a defined volume? Yes, this solid sample takes up some space. So we know, and we're looking to find the volume of solid using this method. Now, after we have finished adding our solid to this graduated cylinder, the water level has risen. The solid takes up space and the water is displaced. So we have the volume before and after we added the solid. So then, if we take the difference between the final and our initial volume, what does that give us? The solid, yep, the volume of the solid. So with this information in mind, let's just write up here, we know our mass is 7.20 grams. And now I'm going to clear off this space so we can do a volume calculation. Because if we want to calculate the density, we need the mass and the volume. Okay, so let's calculate the volume. So we're going to take our final volume, which is 18.4 milliliters, and subtract our initial volume, which is 15.6 milliliters. Again, since we are doing a subtraction operation, what do we care about? Decimal places. So how many decimal places do we need to retain? 1. Okay, so let's punch that into our calculator. So we're going to take 18.4 minus 15.6, and that gives us 2.8. So let's write that down. 2.8. Does it have the correct number of decimal places? Yep, 1 decimal place. We're good to go. So then, do we have enough information to calculate the density? Do we have the mass and the volume? Yes. So let's clear up some space. Let's clear up some space now, and let's write and summarize our data. So we have the mass of 7.20 and a volume of 2.8 milliliters. If density is equal to mass over volume, we're going to take 7.20 grams over 2.8 milliliters. And now this is where we need to be a little careful. When we are dividing quantities, what do we care about? Sig figs. And how many, what's the least number of sig figs between these two numbers? 2. So our answer should have how many sig figs? 2. So let's punch this into our calculator. So we're going to take 7.20 divided by 2.8. And that gives us 2.571. I'm going to write this out longhand, 2.571 gram per milliliter. And now we have to round this number to how many sig figs? 2. What's the second significant digit? 5. Okay, so I'm going to change colors so we can see this. Well, I'm going to change the pen color more accurately. Okay, we look to the right. Is 7 greater than or equal to 5? Greater. So do we round up or down? Up. So our density would be reported as 2.6 gram per milliliter. So I really encourage you to draw pictures. It helps you visualize what data is being collected, what's being done in the experiment, and what do all of these numbers mean, right? If you draw up the picture before and after you add the solid, you can clearly see you're doing some sort of water displacement experiment, and you're able to figure out the volume of your solid. The mass of your sample is obtained via difference, and that's a common operation that you'll do a lot in the laboratory. Any questions on this example? You should be comfortable performing this procedure in lab, as you will do this in one of the labs coming up, and you should be comfortable with density calculations. Okay, the last problem on this quiz is just a check to see if you're comfortable with all of our subatomic particles. The first subatomic particle is the proton. The proton has a positive charge, and it has a mass of approximately 1 AMU. Remember, as we discussed last time, I'm not looking for exact numbers in grams, I'm looking for relative masses. If you tell me protons and neutrons are about the same mass and they're heavier than an electron, you're on the right track, okay? So protons are positive, they have a mass of about 1 AMU. A neutron, do neutrons have a charge? Neutrons are neutral, so you can put it as a 0 or say neutral. Both are fine. And the mass is approximately 1 AMU. Protons and neutrons make up the majority of an atom's mass. Finally, probably the most important particle is the electron. And what is the charge of an electron? Negative, exactly. And the mass is about 10 to the negative 4th AMU. As long as you're indicating electrons are substantially less heavy than protons and neutrons, that's a reasonable answer. You just want to get a sense of these qualitative trends, and you definitely need to know the charges, as we're going to start counting and continue to count protons, neutrons, and electrons in isotope notation. And counting electrons is a critical skill that you'll need for later parts of this class. Any questions on this quiz before we move on and continue our lecture? Okay, let's continue on then. So, we last left off using isotope notation to calculate the number of protons, neutrons, and electrons in atoms. So as a refresher, I'm going to start us off, and I will do this first example. We're going to break down this atomic symbol in isotope notation, and we're going to count the number of protons, neutrons, and electrons. So to help us along with this process, first and foremost, let's identify each of the provided numbers. So first and foremost, as a refresher, the mass number, which is this number in the upper left-hand corner. What does the mass number tell us? Protons and neutrons. The mass number is equal to, and I'm going to use special color coding for this, as you'll see why in a moment. It's equal to the protons plus the neutrons. And let's give neutrons a purple color. Okay, perfect. Let's now look at the number in the bottom left-hand corner. The atomic number, which is shown in the bottom left-hand corner, and is also given by the atomic symbol, corresponds to what? Atomic number? Number of protons. It's what makes an element an element. Each element symbol has a unique atomic number. So the atomic number would be 35 in this case. So how many protons do we have? 35. Ergo, so we have 35 protons, which we write as P plus or just P. Both are fine. Now, let's take a look at this number provided in the upper right-hand corner. What do we call this number in the upper right-hand corner? The charge. So this is the charge. And the charge, as we discussed last time, is essentially the total charge of all of the particles found in our atom. So the charge is equal to, and let's use a different color for electrons, it's equal to, let me write this out this way. So electrons are negative, so we're going to subtract the number of electrons. Electrons are negative particles, right? And then for our charge, we're going to take the number of protons minus the number of electrons. So what we're saying is we're adding up all of our positively charged particles and subtracting all of our negatively charged particles. Now, considering that we have a charge of -1, what does this tell us? Do we have more protons or electrons? Electrons. We have more negative particles. Now, what we're going to do is we're going to take each of these equations and we're going to rearrange them. So let's rearrange our charge equation and let's solve for our number of electrons. So our number of electrons is equal to the number of protons minus the charge. Okay, so do we have all the information we need to complete this calculation? Yes. So for our number of electrons, how many protons do we have? How many protons are we working with? 35. Okay. And then what is our charge? What is the exact value of our charge? Yep. Not more than just 1. What's the magnitude? What's the sign? -1. Don't forget the sign when you're talking about the charge. Okay, so from this information, that tells us that for our number of electrons are equal to 36. Perfect. So we figured out the number of electrons in this compound. We can do a similar calculation involving the mass number. We can rearrange this equation to solve for the number of neutrons. And in this case, the number of neutrons is equal to the mass number, which we'll write in color code. What's the mass number in this case? Oh, why is that opening up? What's the mass number? 81. So we take our mass number of 81 minus the number of protons. And how many protons do we have? 35. Perfect. So if we punch that into our calculator, or if we do it in our heads, you should end up with a number of neutrons of what? 46. Exactly right. Remember, our number of neutrons is equal to our mass number minus the number of protons, which in this case is 46. Does that analysis make sense to everyone? Now, we've done this example involving iron last class session, but what I want us all to remember is, if I just give you the atomic symbol, where do we get the atomic number from? Periodic table. And to show this for iron, let's go over to our periodic table. Let's zoom in to iron. And as we see from last time, we've already circled iron. And what is the number above iron's atomic symbol? What is iron's atomic number? 26. So you can get the atomic number from the periodic table. Okay, with that refresher out of the way, what I'd like you now to do is to tackle this next problem. So instead of decomposing isotope notation into protons, neutrons, and electrons, let's try doing this in reverse. Let's try going from protons, neutrons, and electrons and writing a valid isotope symbol. So I'd like you to give a first attempt at this, and then we'll come together to discuss. Any questions? Okay. Any questions? Okay. Oh, there are also versions that are turned over on other parts of the notes. Any questions? Let's see. So, yeah, mass number looks right. Yeah, looks perfect. Any questions? Yeah, looks good. Any questions? Looks good so far. Yep, looks good so far. Any questions?
I'm just ready.
And the trick is you're going to use each of these equations to figure out and fill in each of these three symbols.
Okay. Thank you.
Any questions? Very, very, very close. So then the number in the bottom row, is it the number of neutrons or protons?
Neutron.
In the bottom row? Protons, yeah. But otherwise, it looks really good. So let's come together to discuss how you go about solving these problems. So first and foremost, I always like to start with the number of protons. I always like to start with protons. They're central to determining what? Why do we care so much about protons? What does the number of protons tell us? Atomic number, which tells us what? It tells the element, the atomic symbol. Okay, so we know at bare minimum for our mystery element, we're going to have an atomic number of 26. We have 26 protons, and wow, that does seem familiar, as lo and behold, an atomic number of 26 corresponds to what element? Iron. So what symbol should we write? Fe. Yep, the same symbol for iron. Okay, so far, so good. Our next step is to calculate the mass number. Our next step is to calculate the mass number. And the mass number is equal to what? What two quantities do we add together? Protons and neutrons, the particles with large mass in our atom. So we take 26 protons, and how many neutrons do we have? 30. Yep. So we take 26 protons plus 30 neutrons, and that gives us a mass number of 56. Does that make sense to everyone? Okay. So our next step is to figure out the charge, and I'm going to switch colors for this. So for our charge, what we're going to do is we're going to take all of our positive particles and subtract the number of negative particles. How many positive particles do we have? How many protons do we have? 26. Yep, so we're going to take 26 protons. And how many negative particles? How many electrons do we have? 24, exactly. Oh, whoops, sorry about that. So we have 24 electrons. So 26 minus 24, that gives us a charge of positive 2. Let's just do a mental check for a moment. If we have more protons, more positive particles, will we have a positive net charge? Yes. It's always important to have these mental checks just to make sure your answer isn't unreasonable. Okay, so this would be Fe 2 plus. If you wrote it as plus 2, there's no problem with that. This is just a stylistic thing that will develop. Charges, you typically write the number followed by the charge. Oxidation numbers, you put the symbol followed by the number. We'll talk about that when we reach chapter 4 in this class. Any questions on this example? Okay, we're going to be doing a lot more practice on this because it's a critical skill that you need to develop. So, what I'd like you all to do now is to tackle the following 2 examples. Tell me the number of protons, neutrons, and electrons in each of these isotope symbols. And there's a copy of the periodic table in your notes and on the board. This is why I would highly suggest you bring a copy of the periodic table to each class session, as we use it a lot. Oh, okay. Yeah, oh, no problem. Any questions? Yeah, looks good so far. Any questions? Any questions?
No.
Okay. Any questions?
No, not yet.
Yep, looks good so far. Yep, looks good so far. Any questions? Oh no, it's perfectly fine to be working on it. They look good so far. Any questions? Any questions? Looks good so far. Any questions? It looks good. So I've seen a lot of reasonable responses, and don't worry too much. If you're able to get the first one done, you're perfectly on track. I just want us to talk about these examples as a class so we can showcase as many examples as we can. So, dissecting bromine 79, first and foremost, if we are given the atomic symbol, what information does that provide us? The atomic symbol tells us the number of protons because we can figure out the atomic number by looking at the periodic table. So, breaking out our periodic table and finding bromine, we see bromine has an atomic number of what? 35. Perfect. So then we know that we have 35 protons. So atomic number of 35, our number of protons is equal to 35. Okay. Now, what number do we need to care about if we're trying to figure out the number of neutrons? Atomic, more specific than atomic mass, what do you call this number up here? It's related to the atomic mass. It's called just the mass number. The reason why I'm making this distinction is atomic mass is another number that you get from the periodic table. This is known as the mass number, but you're on the right track. So then, to calculate the number of neutrons, all we have to do is take our mass number, which is 79, and then subtract from it the atomic number, which is 35. And that in turn gives us 44 neutrons. Now finally, what is the charge of this molecule? What is the charge? What's the charge of this bromine atom? Sorry. Is there any number? No. So the charge is equal to 0. So the charge is equal to 0, and that's equal to the number of protons minus the number of electrons. So if we rearrange this equation, we see that the number of protons equals the number of electrons if your atom is neutral. So then, how many protons do we have? 35. So how many electrons do we have? 35. So we have the same number of protons and electrons if your atom is neutral. This is an important shortcut. Saves you having to do math. You can just quickly write out the number of protons and then write out the number of electrons for your neutral species. Okay, let's tackle this next example, which is a barium isotope. Barium is quite an interesting element, and we'll be handling solutions involving barium 2+ ions throughout this semester. Now, would someone like to tell me, if we take a look at the periodic table and try to dissect this atomic symbol, what is barium's atomic number? What was that? 56. Let's show everyone in the class where we obtain that number. If we break open the periodic table and we go and find barium. So let's find barium. What is barium's atomic number in the periodic table? 56. I'm just always trying to make the point, these numbers don't just come from space. They're numbers that we can obtain from the periodic table and then we have tabulated. Okay, so then we know that our number of protons is equal to 56. Do we have the mass number? Do we have all the information we need to figure out the number of neutrons? Yes. So then our number of neutrons is equal to our mass number, which is 138, minus our atomic number, which is 56. Again, to figure out the number of neutrons, we take the mass number minus the number of protons. And if we punch that into our calculator, we'll get 82 neutrons. Now, is this atom neutral? Are we dealing with an atom or an ion? Ion, okay? So in this case, our charge, which is equal to 2+, is equal to our number of protons, which is 56 protons, minus the number of electrons. Now, if we rearrange this equation, we see that our number of electrons is equal to our number of protons, which is 56, minus the charge, which is +2. And that gives us 54 electrons. Does that make sense to everyone? You're using the same overall procedure and formula to break apart symbols in isotope notation, but it's really critical that you're able to quickly count electrons. This is probably the important skill that we're going to be going back throughout this course. Okay, I'd like you all now to take a moment and I'd like you to tackle these next two examples. The first of which is a relatively infamous or famous, depending on your perspective, isotope. The second sample is a common ion that you observe in compounds with very interesting properties and reactivity. Everything going on? Okay. Everything going on? Yeah. Yep, that's good. Oh, what is this? Oh. You subtract that out. Yeah. Any questions? Next. Oh, okay, perfect. And you're going to see symbol for the number 92. And as you go down the periodic table, the number increases. Yep. Everything going okay? Yep, exactly. Any questions?
I got a question. What is N14?
We'll talk a little bit about that notation, but essentially the 14 is representing the mass number. Yep. Any questions? Looks good so far. Any questions? Yeah, looks good so far. Very close. So to calculate the mass number, you add up protons and neutrons. Yep.
Okay.
So I saw a lot of reasonable answers for this infamous isotope question. And for those who are familiar with world politics and world news, an element with 92 protons, or an atomic number of 92, is uranium. So let's talk a little bit about where did I come up with uranium. So if I go to the periodic table and I scroll down, the periodic table is arranged in order of increasing atomic numbers. So I'm going to look for elements far down on the periodic table. I find the atomic number 92, and we see the symbol for uranium. Yep. Okay, perfect. So we've established the first portion of this problem. Now, given that we have the number of protons and neutrons, what can we calculate using that? Mass, yep. Or more specifically, the mass number. So the mass number is equal to our 92 protons plus 143 neutrons. And that in turn, that I'm going to have to break out the calculator for just to be sure. So we take 92 plus 143, and that gives us 235. Again, there's no shame in breaking out a calculator when you want to be sure about an addition or subtraction operation. I'm not looking over your shoulder seeing how many times you've used your calculator. So let's enter our mass number of 235. And now, given the number of protons and electrons, can we figure out the charge of this species? Yes. So our charge is equal to our number of protons minus our number of electrons. And 92 minus 91 gives us a charge of +1. You always want to make sure you're noting the magnitude of the charge, whether it's positive, a cation, or negative, an anion. Perfect. So let's talk a little bit. Any questions on this example? Don't be shy to ask questions. We're going to be doing, yes?
It's not necessarily an example, but earlier you made a distinction between mass number and atomic mass.
We'll talk about that in about 10 minutes.
Okay.
Yes. So let's talk a little bit about another way that isotopes are represented and expressed. So many students were looking at this N14 and were a little bit confused. What does that mean? Well, when you write out an isotope in this form, this number 14 represents your mass number. So you can think of it a little bit as if we wrote out the following symbol. So the number after the dash is your mass number. do these two symbols provide the same level of information? Do they provide you the same information? Yes. Both are equally easy to say, but this is certainly easier to type longhand. These are the two ways that we express isotopes via isotope notation. So the number after the dash is your mass number. So with that information in mind, what I'd like you all to do is to tackle these next two examples involving dash notation and figure out the number of protons, neutrons, and electrons. Yep, that's good. Any questions? Okay. Yes.
So it's not necessarily understand. It's just the element.
Yep. Any questions? Looks good. Looks good. Any questions?
Thank you.
Okay. Any questions? Okay. Any questions?
No.
Okay. Any questions? Everything going okay? Yep, so that's the full symbol. And now try to decompose it into protons, neutrons, and electrons. Any questions? The first part looks good, and we'll talk about this one in a moment. Okay. Any questions? Yep, it's good so far. So let's now take a moment and let's talk about these next two examples. So the first nitrogen 14 example, you should be comfortable completing. This second example involving silicon 28 is a bit of a stretch, and we'll talk about both as representative examples. So looking into the periodic table, what is the atomic number? How many protons does nitrogen have? 7. Yep. Where did we get that? If we break out our periodic table and we go and find nitrogen, lo and behold, as I've circled multiple times, nitrogen has an atomic number of 7. Again, always make sure you're referring to the periodic table. It's an invaluable resource. What else are we given about this specific ion? What is the charge? -3 or 3-. Okay? Actually, yeah. Okay? Now from here, how many protons do we have? 7. Our number of protons, which is equal to our atomic number, is 7. Given that we know the mass number, can we figure out the number of neutrons? Yeah. So our number of neutrons is equal to our mass number of 14 minus our number of protons, which is 7. And that gives us a total of 7 neutrons. Finally, since we know the charge, can we calculate the number of electrons? Yes. So the number of electrons is equal to the number of protons, which is 7, minus the charge, which is -3. And remember, when you're subtracting a negative number, that's the same as addition. So that gives us a total of 10 electrons. Perfect. So we've completed this example. Now, there are other ways to write problems that test your knowledge of isotope notation, and I will showcase this first example as a representation, and you'll be able to practice this on a few more examples. So, we're asked in this problem to write the isotope symbol for an isotope of sulfur that has the same number of neutrons as silicon 28. Okay, so let's unpack this problem. So we're given that we have silicon 28. Okay? And what do we need to know about silicon-28? What do we need to know for this problem? Just even more basic than that. What is the problem asking us to figure out as an end goal? Neutrons, right? So we want out of this silicon-28, we want to eventually figure out the number of neutrons found in silicon-28, right? So with that end goal in mind, what information can we get from this symbol? What was that? Protons, yep. We can go and find the atomic number. So let's do just that. Let's go to the periodic table. We found silicon, and what is silicon's atomic number? 14. Okay, perfect. So then we can fill that in, and from the mass number and the atomic number, can we figure out the number of neutrons? Yes. So we're going to take 28 minus 14, and that gives us 14 neutrons to work with. Okay, that's the first part of this problem done. This problem is asking us to write the symbol for an isotope of sulfur. So what atomic symbol am I going to write? S. S for sulfur. Okay, what do we know immediately about sulfur? What piece of information can we figure out? The atomic number, exactly, the number of protons. So if we go to the periodic table, one moment, what is the atomic number for sulfur? 16. Yeah, let me just move this a little bit so it, oops. There we go. So sulfur's atomic number is 16. So that tells us we have 16 protons in sulfur. Now, in order to complete this isotope symbol, what do we need? Mass number, yep. And do we have enough information to calculate our mass number? Yes. So to calculate our mass number for this sulfur isotope, we're going to take the number of protons, which is 16 protons, plus the number of neutrons, which is 14 neutrons. And we know that this sulfur isotope has 14 neutrons because the problem asks us to write the atomic symbol for a sulfur isotope with the same number of neutrons as silicon-28. So that gives us a mass number of 30. And this is our final answer. We could also write this as S-30 if we felt so inclined. Does that make sense to everyone? Okay. To test your understanding of these types of questions, what I'd like you to do is to try and write the isotope symbol for an isotope of copper that has 3 more neutrons than copper 63. And try to think a little bit about how we write isotope symbols, as there's a fast, really, really fast way to do this problem. Any questions? Looks good so far. Any questions? Looks good. Any questions? Yeah, looks good. So I saw a lot of reasonable answers. Everyone's pretty fast at this. And the reason for that is there's a trick for this problem. So looking at copper 63, let's think a little bit about what does the mass number represent. So the mass number is what 2 things added together? Protons and neutrons, right? So the mass number is the number of protons plus the number of neutrons, okay? Now, if we have 3 more neutrons, what are we adding to our mass number? If we have 3 more neutrons, what are we adding to our mass number? If we have more neutrons, does our mass number increase? Yes. So if we have 3 more neutrons, what do we add to this mass number? 3, exactly. Okay, so 63 plus 3 gives us 66, right? So this would just be copper 66. You can also write this in the classical form as copper 66. Does that make sense to everyone? So always just think, what do these equations represent? Is there an easier way to do this than just decomposing this to protons and neutrons and then adding 3? Yeah. Okay, so any questions on dissecting isotope notation? Okay, counting electrons is a critical skill. I can't emphasize this enough. So with that out of the way, let's now move on to our next few topics. So one of the classic experiments that Rutherford performed to identify the presence of protons in our atoms involved this experiment where he took nitrogen-14, bombarded it with an alpha particle, and out was generated an oxygen-17 isotope and a proton, a hydrogen nucleus. So what I want you to do is to dissect each of these isotope notation symbols and tell me the number of protons, neutrons, and electrons in each. This is more practice for reading isotope notation. So let's take a few moments to handle that, and I'll rewrite each of these symbols that I'm asking for you to dissect in a bit larger font, so that way everyone in the back can see. There, oh, whoops, that should be helium. Perfect. So these are the 4 symbols that I want you to tell me the number of protons, neutrons, and electrons for each of these species. Any questions? Looks good so far. Any questions? Everything going on? Okay. Everything going okay? Okay. Any questions so far? Okay. Any questions? Looks good so far. Any questions? Yeah, looks good. Any questions? Yeah, looks good. Good. And we'll discuss this in about 1 more minute. Very good. Perfect. So let's discuss this next example set. And everyone's getting quite fast at this point. It's good. The more practice you do, the faster you're able to go through calculations and process problems. So let's start with nitrogen-14. Let's start with nitrogen-14. If we look in the periodic table, what is nitrogen's atomic number? 7. We've seen that a ton of times in this lecture. Okay, so how many protons does nitrogen-14 have? Or how many protons does nitrogen in general have to its name? 7. I've conveniently given you neutral species. So what do we know about the number of electrons? Is it going to be the same or different? The same, exactly. Finally, for our number of neutrons, since we have the mass number, all we have to do is take our mass number minus the atomic number. 14 minus 7 gives us 7. Any questions so far? Let's now dissect helium-4, which is otherwise known as an alpha particle. How many protons do we have in helium-4? 2. how many electrons do we have in this neutral species? 2. And how many neutrons do we have? 2. Symmetrical in a way. 4 minus 2 gives us 2. Okay, let's continue on now. Oxygen 17 is the first new isotope symbol that we've seen. So we're going to have to go to our periodic table. So looking at oxygen, one moment. What is oxygen's atomic number? 8. Okay, so how many protons does oxygen have to its name? 8, exactly. Since it's neutral, and only because it's neutral, how many electrons do we have? 8. And finally, for our number of neutrons, we take 17 minus 8, which gives us 9. Yes, if I wanted things perfectly symmetrical, I'd have you do oxygen 16, but I want to make sure people know how to write protons, neutrons, and electrons and not just write the same number for all 3. Okay, let's look at hydrogen 1. How many protons do we have in hydrogen? 1, yeah. A proton is also known as a hydrogen 1 nucleus with no electrons. How many electrons do we have for this specific symbol? Since it's neutral, how many electrons do we have? 1, yep. And then how many neutrons do we have? 0, because we take our mass number, which is 1, minus the number of protons, which is 1, and that gives us 0 neutrons. Protons are just a hydrogen nucleus. Okay. So, any questions on this example? We're next going to talk a little bit about isotopes and their role in nature and what exactly the atomic masses that you see in the periodic table mean. So, as a refresher, isotopes involve the same element, atomic number, but they have a different mass number, and as a result, a different number of neutrons. So, for example, oxygen 18 and oxygen 16, both of these isotopes are of the same element. They're both oxygen, but they have different masses, different mass numbers. Does that make sense to everyone? Okay. Now, we can identify and quantify the amount of each isotope in a sample of an element using a technique known as mass spectrometry. And the way that mass spectrometry works is you take your sample, it becomes ionized, charged, and then it's passed through a series of plates and magnets. And based on the particle mass, we get separation of particles based on their mass. So what a mass spectrometer allows us to detect, quite simply, it allows us to detect the mass to charge of an atom, or more specifically, of an atomic or molecular ion. And as an additional piece of information, the mass spectrometer also tells us the relative amount. So this intensity tells us the relative amount of each ion. So, considering that isotopes have a different mass, can we separate isotopes and identify different isotopes using mass spectrometry? Yes, because it separates and distinguishes atoms and ions based on their mass. This intensity tells us the relative amount of each ion, which in turn can tell us the relative amount of each isotope. So we're going to look at a few pictures of mass spectrometry data collected for different elements, and we're going to try to see what isotopes are present and in what amount. Does that make sense to everyone? Okay, so let's take a look at a few pictures. So, isotopes are present in different abundances in nature. We don't have exactly equal amounts of each isotope. Depending on the element, different isotopes predominate. For example, carbon consists of carbon-12 and carbon-13. Carbon-12 is roughly 99% of all carbon atoms in our universe. Carbon-13 is a relatively minor isotope, consisting about 1% of all carbon atoms. If we were to visualize this using a mass spectrometry output, so if we're looking at mass over charge as a function of intensity, considering that carbon has 2 isotopes, how many unique mass peaks will I see? How many unique masses? 2. Will one of those peaks be way larger than the other? Yes, substantially so. So if we were to draw our output, we'd have a mass over charge of 12 and then a tiny little peak indicating our mass over charge of 13. And a key feature of this output is that the ratio of these 2 peaks gives us a sense of the ratio of the 2 isotopes in nature. Does that make sense to everyone? So, another example that I want us to look at and to test that we're comfortable with this idea, I'm going to show you now an output for chlorine. So here's our mass to charge, here's our intensity, and let's show the 2 major peaks. So this has a mass to charge of 35, and this smaller peak has a mass to charge of 37. So from this picture, this is an output that you'd see if you analyze chlorine gas via mass spectrometry. About what is our major isotope? What's the most predominant chlorine isotope? 35. This mass to charge gives an indication of the mass number of that isotope. So for chlorine, we have 2 isotopes, chlorine 35, and what's our other isotope? What's the other isotope? 37, exactly. Now, if we had to qualitatively assign percent abundance, which of these 2 isotopes is more abundant in nature? Which one has a larger peak? 35. And about how many times larger is this 35 peak compared to the 37? 2 times, 3 times, 4 times? Just an estimate here. About 3 times, yeah. So chlorine, 75% of all chlorine atoms are chlorine 35, and 25% of all chlorine atoms are chlorine 37. The reason why this is important is what we've established is for a given atom of an element, there are different isotopes. And those isotopes are present in different amounts in nature. And where this really comes to head is when we start to take a look at these atomic symbols in our periodic table. And let's really ask ourselves, what does this bottom number really mean? What is this bottom number represent? And I'll tell you, this represents the average atomic mass. Now, that name in and of itself is indicative of the issue here. What do we mean by average? The average of what? Do all chlorine atoms have the same mass? No. So this is the average of all of our isotopes. So the atomic mass that you see in the periodic table is the average mass of an atom, of an element, weighted by the abundance of each isotope. Would it really be fair if we wanted to take the average, for us to just take 35 plus 37 and divide it by 2? Is that a fair average, considering we have so much more chlorine-35 in nature? Would this account for the true amount of each isotope in nature? No, this would not be correct. There are not equal amounts of chlorine-35 and 37. So to average out all of our isotopes found in nature and to account for their abundance, we use what's known as a weighted average. So let's show our equation for the atomic mass. So we're taking a weighted average here. So this is a weighted average of the mass of all isotopes, accounting for their percent abundance. So the way that we go about doing this when calculating the average atomic mass is this sum symbol means sum, and it quite simply means you're adding up all of the quantities. So when you're calculating the average atomic mass, you're going to plug in the mass of your isotope, which you'll be given. And to account for the abundance in nature, you're going to multiply it by the percent abundance divided by 100. And you're going to do this for every single isotope of that element. So for example, you'd add the mass of your second isotope, etc. And you'd repeat this addition process until you've added up the mass times the percent abundance of every single isotope. Does that process make sense? Let's showcase this in practice. So let's calculate the average atomic mass of chlorine using this formula. So let's write down our data here. So for chlorine-35, what is the mass of chlorine-35 given in this problem? What is the mass? 34.97. The actual atomic mass of an isotope is going to be a little bit less than the mass number. So you're always going to use the given atomic mass. Okay, what is the percent abundance? What is the percent abundance of this chlorine-35? What's the natural abundance of chlorine-35? Yep, 75.78. Okay, perfect. Sorry about that. Okay, let's write out our data for chlorine-37. What is our mass for chlorine-37? 36, yep, 36.97 AMU. And what's the percent abundance? 24.22. As a nice little sanity check, these 2% abundances, if we've accounted for all of our isotopes, should both of these percentages add up to 100? Yes. If we've accounted for all the isotopes, which we have, all the percent abundances, when added together, would give us 100. Okay, so now that we have our raw data, let's punch this data into our formula. So the mass of chlorine is going to be equal to, and let's change colors for this. Let's start by calculating and scaling the mass of chlorine-35. So what's the mass of chlorine-35? Yep, so we're going to take 34.97 AMU. So this is all of our calculations for chlorine-35. And now what is the percent abundance of chlorine-35? Yep, 75.78. And we're going to take this percentage and we're going to divide it by 100%. Okay, so this is the portion of our calculation for our first isotope, chlorine 35. Let's do the exact same process for chlorine 37. We're calculating, we're taking the mass and multiplying it by the percent abundance, and we're doing this calculation for each isotope. Okay? So what's the mass of chlorine 37? 36.97. Yep. Okay, and what is the percent abundance of chlorine 37? Yep, 24.22%. And then we're going to divide this by 100%. So as you notice, we're repeating the same basic calculation. Mass times percent abundance over 100 for each isotope. And we're adding the results of each of those calculations together. Does that make a lot more sense on how this equation works? Okay. Have we accounted for both of our isotopes? If we had 3 isotopes, would we have to have another one of these sections, another one of these calculation portions? Yes. Okay, now we're ready to enter this into our calculator. So let's switch to that. So first things first, I'm going to enter 34.97. Okay? And what are we multiplying it by? Yep. So we're going to multiply it by 75.78, and then we're going to divide by 100. So entering this into our calculator, we're going to hit the multiplication symbol and enter 75.78. Okay, so you should end up with about 2,600. Everyone okay with their calculator? We're next going to divide by 100. Okay. Now, just as a note-taking method, I really like to just write down what number I get from each phase of the calculation. Just so that way, if I make a mistake with my calculator, I don't have to start from scratch. Okay. Now, in our next step, what are we doing? Are we adding, subtracting, multiplying, dividing? Adding, right? So we're going to hit on our calculator the addition symbol. So you're going to hit the addition symbol, and then you're going to hit the parentheses, because we're going to do a new calculation. Everyone following so far? Okay. Now, what are we doing for our second calculation? We're going to take this 36.97 and multiply it by what? 24, and then divide by 100. So let's execute on that. So we have 36.97 times 24.22 divided by 100. And you should get 35.45 at the end of your calculation. Did that match? Okay. And so then we can report our final mass of chlorine, the average atomic mass of chlorine. So the atomic mass of chlorine is equal to 35.45 AMU. Does that make sense to everyone? We're going to be doing a lot more of these calculations next class session. And if we have extra time, we may lecture in lab today as well, depending on how long today's lab takes. Key features to note. What are the units of the atomic mass in the periodic table? What are the units? AMU, atomic mass units. It's not grams yet. It's AMU. And let's be really specific here. What is this the mass of? Fundamentally, what are we looking at? The mass of what fundamental particle? What are we looking at? What is this the mass of? A chlorine, and more specifically, what about a chlorine? A chlorine atom. So just to keep this in mind, this is AMU per atom. So if we look at a chlorine atom, on average, the mass is equal to 35.45 AMU. This is an average. The exact mass of an individual atom may be a little bit higher or a little bit lower, depending on which isotope. But the key thing, just remember the units are AMU per atom. Okay, we'll be having a few practice examples on this. If you're looking at the pre-lecture assignments, you'll be doing a lot of calculations inspired by this equation. And next class session, we'll be manipulating this equation to calculate percent abundance and get even more information about the isotopes of each element. Okay, if that's it, I'll see you in lab in a few minutes. Yes.
So over here,
Yeah.
I wrote down all the digits, but we got ultimately 4 significant
Yes. We truncated because these have 4 significants.
Okay. What we also have the percentage at 6 figures.
Yes, but this is 4 significants. So not
Okay. Also, so I now understand that the atomic mass is that average.
Yeah.
What determines the mass number? How do we decide?
The mass number is the exact number of protons and neutrons in that isotope.
Oh, okay.
Does that make sense?
So can we get a mass number off of the atomic mass?
No.
Okay.
Yes.
All right.
Yes, you can.
Okay.
So one thing I do want to show you is, one moment. Okay.